Hi there, my name is Aaron Lanterman. I'm a professor of electrical and computer engineering at Georgia Tech, and in this lecture of GPU programming for video games, we'll look at a custom forward scriptable render pipeline. And the next lecture, we'll look at a custom deferred scriptable render pipeline. If you want to run the demo I'm about to show you yourself, you want to go to the 4795 archive on my GitHub, and let's see if we scroll down a bit, you'll see GPU23 SRP forward.unity package. That's what you want to get. So I'm going to make a new project here, and it's going to be a basic 3D project, and let's call it SRP forward demo. You could call yours whatever you want. Before I import that Unity package, I want to go to Window, the Package Manager. In the upper left corner here, let me go to the Unity registry, and I want to look up the core RP package. So this is all the basic stuff for the scriptable render pipeline. If you're using a universal render pipeline or the high definition render pipeline, you can import the packages for those, and I think those will automatically install the core RP library. But here I just need the core RP library. And surprisingly, although the URP and the HDRP have changed a lot with individual releases from year to year, the core RP library has remained fairly stable for a while. The demo I'm about to show you, I actually created back in 2019. Okay, let me take my GPU23 SRP forward Unity package and drag that onto the assets folder here. Yep, let's import all of this stuff. Now, you don't have to import the core RP library before importing the Unity package. But if you import the Unity package first, Unity will give you a whole bunch of error messages. You'll then have to import the core RP library and then do re-import all. So let's go to Scenes and look at this SRP intro scene. And you'll see that I have a red sphere, a blue sphere, and the blue sphere is translucent. But over here, we have some black spheres, and these should not be black. What's happening is this has some shaders designed for the scriptable render pipeline, but we're still using the built-in pipeline. So we need to go to Edit, go to Project Settings, and we need to do a couple of things. The first thing we need to do is go to Player and select the linear light space, as we always do, because linear is good and gamma is bad. Let's also go to Graphics. Notice I have this thing here that says Scriptable Render Pipeline Settings, and it says None. So it's defaulting to the built-in pipeline. So let me click over here, and we'll select My Custom Pipeline. Changing the pipeline, yep. And if we do that, we'll go over here, and we see that there's some nice spheres. And if I press play, you'll see that I have one of the lights is animated by a little script that just moves the lights back and forth. And this also works in the scene view. Let me zoom in a little bit here. There you go. Notice our SRP shaders work both in the game view and in the scene view. There's a little bit of extra work needed to make this work in the scene view. Well, not really extra work, it's just a couple of lines, but it's something you need to do. I'll talk about that later. So I told the graphics engine in Unity to use my custom pipeline, and that's this little weird little symbol here. Let me click on that. We see that it has a couple of options for dynamic batching and instancing. These are various optimizations that the Unity renderer can implement in some instances. So you can turn them on or you can turn them off. For the purposes of this class, I don't want to get too much into the details of these things. We'll just talk about how to set up things in order to support them. Now, I included this My Custom Pipeline asset in the Unity package, but if I hadn't done that, what you can do is you can go to the plus sign here, and you can go down to this rendering menu and select My Pipeline. Now, this doesn't come with Unity. I included some code that puts this entry into the asset creation menu. And selecting that, I now have a new My Pipeline. Notice the new pipeline has dynamic patching and instancing defaulting to off. So if I want, I could switch those on. The code I'm about to show you is pretty much taken straight from the scriptable render pipeline tutorial on the Catlike Coding website. Notice this particular tutorial is for Unity 2018, so it's really kind of remarkable that this code works in 2023. It's been a while since I made this demo, so I can't remember if I had to do any tweaking on it to get it to run. There's a note here about this series being removed shortly, and it says go to the custom SRP series instead. So that's a newer tutorial. For pedagogical purposes, I'm sticking with the older tutorial because while the newer tutorial has better software engineering in the sense that things are broken out into functions, etc., for my current pedagogical purposes, it's convenient to have the code as tight as possible, so I think the older code actually works better. The entire Catlike Coding website is an absolute goldmine, so I suggest checking it out. So taking a look at the scene here, we have 5 spheres. Now, 2 of the spheres are using what I call the Unlit shader, and those are just producing colors. And 2 of the spheres here are actually reflecting light. Well, actually 3 of them are reflecting light. But notice that only 3 of the spheres, the 3 in the back here, are opaque, and the 2 in front are transparent. Notice that I don't have to have different shaders to handle transparent and opaque objects, and let me show you what's going on there. So if I scroll down a little bit here at this particular material, you'll see that we have this source blend and this destination blend and the Z-write. So Z-write indicates whether we're writing into the Z buffer, so that's handling obscuration. Now here I have source blend as 1 and destination blend as 0, and you can click on these and set these to all sorts of stuff. What that is basically saying is that when we're writing a color to a given pixel, 0 of the color is coming from the destination, i.e. what's already there, whereas all of it is coming from the source that we're writing to it. So that's appropriate for opaque objects. But if I click on the transparent objects, what I see is that we actually have Z-write being off because for transparent objects, we're not worrying about the Z buffer. And the source blend is set to source alpha and destination blend is set to 1 minus destination alpha. So that allows us to handle transparency effects. So let's start by looking at the shader code. So I'm calling this mylit. Don't get this confused with the lit shader of the high definition render pipeline or the universal render pipeline. This is a much more primitive shader with just 1 color setting. There's no textures or anything else in there. Here we set up some enumerations to select the blend modes and the Z-write mode, and those are just applied right here. So this particular shader is going to use model 3.5. And we need to specify that because Unity defaults to 2.5. So we're going to import this common.hlsl library. That's basically taking the place of the CG includes library that we've used previously with the built-in pipeline. And now we have to get into some Unity-specific weirdness. We're going to use Unity Matrix M and Unity Matrix IM instead of the Unity Object to World and Unity World to Object matrices. And this has to do with some strange stuff Unity is doing with GPU instancing. It might have to redefine these as something else. So we're just going to use these uppercase variables later in the code. Now we do need to declare Unity Object to World and Unity World to Object. Unity will fill this in for us. We're also declaring Unity Matrix VP. That's a combination of the view transform and the projection transform that Unity will fill in for us. So even in the scriptable render pipeline, Unity is filling in some stuff for us. Now the color, that was something we declared in properties. Now the cbuffer start-end blocks here are not things that are required, but it allows Unity to do certain optimizations. For instance, individual objects in your scene may have different object-to-world matrices, but that view projection matrix, that's going to be the same for all of the objects you're drawing in a particular frame. We're assuming here that we have up to 4 lights being rendered, and unlike the built-in pipeline where various different lights were handled in different additive passes, here we're going to handle all of the lights in one pass. So here we have the colors of the lights in an array and these directions or positions where the W coordinate indicates whether it's a point light or a directional light. Now remember, in the built-in pipeline, Unity filled out some lighting information variables for us. Here, we're going to actually have to do that explicitly in our C# script. We're going to have to explicitly set these variables. So for our vertex input structure and our vertex output structure, we have things we've seen before. We're going to take in positions and normals, and here we're going to output positions in clip space and positions in world space, as well as normals. And this is the structure that's handling going from the vertex shader to the fragment shader. So these various quantities here are going to become interpolated. The variable names we're using here differ from those that I've used in previous lectures. I decided to stick with the naming scheme used by Catlike Coding, so in case you go and look at the original code here, things will match up. There is something new and strange here, and that's this Unity Vertex Input Instance ID macro. This is some bit of Unity magic needed for GPU instancing to work. Just put it in your structures and then don't worry about it. So our vertex shader starts with a bit of Unity magic. That's this Unity setup instance ID macro that will tweak things as needed associated with the GPU instancing. Again, don't worry about it. Just make sure that later on you're using Unity matrix M instead of Unity object to world. And similarly, you're using Unity matrix IM instead of Unity world to object. So the rest of this is all stuff we've seen before. We get the position in world space by multiplying our input position by Unity matrix M. Now the input.position coordinates are 4 vectors, and they should be coming in with their W component automatically set to 1. But by putting the 1 here and constructing it this way, that acts as a hint to the compiler, where the compiler now knows that W position is 1, and it can potentially do some optimizations. You don't have to do it this way, but it's kind of nice. We take those positions and assign them in the output structure, and we also take those positions and multiply them by the view projection matrix to get the positions in clip space. So this isn't actually something that's used directly by the fragment shader to compute colors, but of course it's needed for the GPU itself to know where things are going on the screen. Next, we need to transform the normals. And if you need to remember how to do that, you can go back and review this lecture I made called Normal Vector Transformations. So to transform the normal, if we interpret the normal as a column vector, we need to pre-multiply it by the transpose of the inverse of the object-to-world matrix. Now, the inverse of the object-to-world matrix is the world-to-object matrix, but here we're using Unity matrix IM instead of world-to-object, but that's just because of this weirdness of the instancing. Oh, and I should have mentioned that we're taking the upper left 3x3 subset of that matrix. Now, we generally don't see an explicit transpose command used in HLSL code. Instead, we're going to take advantage of the way that matrices are stored in HLSL and realize that if we multiply by putting the vector first in the multiply command, it's like we're taking the column vector and multiplying it by the transpose of this matrix. So here's the fragment shader. As with the vertex shader, we start with this Unity setup instance ID macro. It's just a weird magical Unity thing that deals with GPU instancing. You can take it on faith. All right, so we have the normals coming in, but remember this is coming in through a texture coordinate, and when it goes through the interpolation hardware, there's no guarantee the result is going to be normalized, so we need to normalize it ourselves. There's nothing fancy about this albedo color here. That's just going to be the color we set in the inspector. You could add fancier things to this, like texture lookups or whatever. Now, the final result is going to be this albedo color times this diffuse light calculation that we do in this loop here. The alpha is going to be whatever alpha we choose in the color in the inspector. Now, as far as this lighting loop goes, we're going to deal with all of the lights at once through this for loop, possibly up to 4 lights, assuming we set max visible lights to 4 as we did earlier in the code. But you can, of course, change that. Note that this is a very different way of handling multiple lights than we had in the built-in shader, where each light was handled in a separate additive pass. Okay, so this is a usual diffuse calculation. We're not worrying about specular light here. So we're taking the dot product of the normal vector and the light vector, and we're using saturate here to clamp that between 0 and 1. Now, of course, this computation here shouldn't go above 1, so we could have used max 0, all this stuff instead, but they use saturate, so we'll use saturate. So we'll take that and we'll multiply that by the light color and add that to the diffuse light that we initialized to 0. So what about this light vector calculation? Well, the W component of the light has 0 or 1 in it, and it has 0 if it's a directional light. So if it's 0, this whole second term here winds up disappearing, and we're just left with visible light directions or positions. And for a directional light, this indicates the direction. Now, we wind up normalizing it, and it's already normalized, but normalizing it again doesn't hurt. Now, if it's a point light, this W component has a 1 in it, so we wind up with the position of the light, which is what is stored here, minus the position of the coordinate from the facet in world space. So that gives us our vector pointing from the facet to the light, and we do need to normalize that probably. Now, when we looked at shaders for the built-in pipeline, we could kind of just look at the shaders. But we're dealing with scriptable render pipelines now, so we need some C# scripts to drive all of this. We need a pipeline asset script, and we need a script for the pipeline itself. Unsurprisingly, the pipeline asset script is what you use to make one of these little pipeline asset thingies. And there's not much to that particular script. This is it. So we're using the Unity engine.rendering package that has all of our scriptable render pipeline goodness, and we're inheriting from render pipeline asset to create the myPipeline asset. The actual myPipeline object is defined in this myPipeline script that we'll look at in a second. And all we're really doing here is overriding this method createPipeline that basically just creates one of these myPipeline assets. Now the constructor for the myPipeline asset needs this dynamic batching variable and this instancing variable, and those are just bools that we'll set up here. And those are the bools you see up here in the corner in the inspector. The final important bit is this Unityism here, where we have create asset menu, menu name equal rendering / myPipeline. That is what creates this menu option in the asset menu that lets us create one of these pipeline objects from the menu here. So here's the actual code for the myPipeline pipeline. It inherits from render pipeline, and it goes on for many more pages. This is by far the most complicated bit of C# we've looked at all semester. We'll set this max visible light constant to 4 to match the 4 that we set in the shader. And at this point, we also have some data structures for our light data. So what we have here are the structures on the C# side, but this isn't automatically set in the shader side. We'll have to do that ourselves. Now, in some of the code that we looked at previously, we referred to variables in the shader code and set them by string, but that's not very efficient. So here we're using this property to ID method in the shader class that takes the string and spits back a number, and we can use that number to efficiently assign the variables. So later you'll see code where we copy the C# side light data to the shader side light data. Now there's not much to the constructor. It takes the variables that we pass in when this is executed from the myPipeline asset script, namely these dynamic batching and instancing variables, and assigns those values to the local variables up here. Actually, I didn't do the tabs here very well, did I? Okay, let's put this here, and let's go doot, 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 doot. Okay, I like that better. Yeah, what about that? So every time this comes out, I have to think about things. The dynamic batching and instancing variables on the right correspond to the variables in the parameter list here. This .dynamic batching and this .instancing refer to the variables up here. We're also going to set graphic settings. Lights use linear intensity to true because linear is good and gamma is bad. So what good is a render pipeline if it can't render objects? So to describe how we want to render objects, we want to override this render method. There's an assumption that there might be multiple cameras, so there's a camera array passed in here, and all we're going to do in this particular method is just loop through all of the cameras and then run another render method that just has a single camera in the second parameter. Now, the first parameter is something called a scriptable render context that we're just going to pass along. The scriptable render context is extremely complicated. It basically has all of the data and methods needed to actually render the scene. Before moving on, we'll define a couple of variables. One is a command buffer named myRenderCamera. You can name it whatever you want. So basically, when you're communicating with the GPU, you want to avoid the overhead of setting up just talking to the GPU. So instead of sending one command at a time and having each executed individually, you develop a buffer of commands that get bundled up and sent off and executed in a row. At least that's my understanding of it. Okay, I'm actually not fond of code where you have two words in a row where one has an uppercase and the other word has a lowercase, and that's the only difference, but it is a common coding style and it's what Catlike Coding used, so I'm going to stick with it. Anyway, we're creating a shader tag associated with the shader tag string srp default unlit. So you can define light mode tags in your shader code and be able to select different bits of shader code based on their tags or not. And this one here, this srp default unlit, this is a special one that gets executed when you don't define any shader tags in your code. And in the HLSL code I just showed you, we didn't define any shader tags. So this is a good one to use. Oh, don't worry about the fact that this documentation page here says universal render pipeline. This statement about srp default unlit applies to SRPs in general. Now, don't be thrown by the fact that there's the word unlit here. We are using this in our lit shader. So here's the main guts of our code, the render function for a single camera. Before we do anything else, there's a tweak we might want to do to the scriptable render context that gives it the ability to operate in the scene view. And that's this line here with this emit world geometry for scene view method. Now, we only execute this if the camera type is a scene view camera type. Now, we only need to check any of this at all if we're running in the editor. So that's why this whole thing is wrapped in this if Unity editor bit. And that means that if you're actually compiling this game and running it as a standalone thing outside of the editor, it doesn't waste time doing this check. Next, we're defining this culling parameters variable. That's this very complicated data structure called scriptable culling parameters. So the scriptable culling parameters are basically bits of information from the camera and the scene needed to figure out what parts of your scene are actually visible by the camera. So we go to the camera and say, camera, run your try get culling parameters method. And the culling parameters are actually set by using the out keyword in the culling structure here. And this method returns true or false depending on whether it was successful or not. So if it wasn't successful, we give up and just return and don't do anything. You would probably also want to put some sort of error message on the log or something. Then ask the all-seeing, all-knowing render context to cull the various objects in the scene based on these culling parameters. Now, culling parameters is a big data structure, so rather than pass by value and shoving all that data on the stack, we use ref here to pass by reference, so it's a little more efficient. Culling results contain information about what survived that culling operation. Now, these culling results don't just contain information about what objects are visible. It also contains information about what lights are relevant. So your total scene in Unity might consist of 20 lights, but it's going to give you just the relevant ones as far as lighting the objects in your scene viewed by the camera. Okay, so now what we're going to do is we're going to look at the culling results, find what light survived that process, and then assign the appropriate information to our variables on the C# side. So the first thing we're going to do is actually ask the culling results, how many lights did you find with this .length method? And there's a possibility that there are actually less lights than we have with our max visible lights. Now, you might have actually had more lights survive the culling process than our max visible lights, but we're going to clamp things at a maximum number of visible lights. And that's generally okay because what Unity does is it will order the list of lights, the various arrays we're going to look at here, in terms of order of importance by some criteria Unity has decided. So the most important lights come first in the list, and hopefully the lights that we wind up ignoring in this process are less important. So going through this for loop, we get each of the visible lights from the culling results, assigning those to a light variable. Those are part of the visible light class. And then we'll grab the final color from the light and assign that to the appropriate entry in our visible light colors matrix. Note that the final color is the light color multiplied by the intensity of the light. To get the direction of a directional light or the position of a point light, we need to ask the light about its local to world matrix. So if the light type is a directional type, for directional lights, the light is thought of as pointing down its local z-axis. So to get the actual direction of the light in world space, we need to get the third column, which, since the columns start numbering at 0, we use getColumn2. Now our light vector is supposed to point in the direction of the light, so we need to reverse our vector. Now, for a point light, that's thought of as a translation, so that's going to be in the last column of this world transformation matrix, so we use getColumn3 for that. Now, remember that the W component has 0 in it for directional lights, and it has a 1 in it for a point light, and this works that out automatically because the lowest row of the matrix is going to have a 0 in it in this third column. And again, the numbering here is a little confusing because the numbering starts at 0. Whereas the last column of your world matrix is going to have a 1 in that lower right entry because you need that 1 there for translations to work with homogeneous coordinates. So this works out automatically. I think that's pretty clever. So the next thing we do is we go to our scriptable render context and we ask it to set up camera properties. So what does that do? According to the docs, that schedules the setup of camera-specific global shader variables. This function sets up view, projection, and clipping plane global shader variables. Okay, so now we're going to load some commands into the command buffer. The first one, clear render target, is just going to zero out the Z buffer. The first argument indicates whether to clear out the Z buffer. The second argument indicates whether to clear the color buffer. And notice that's set to false. So it's actually ignoring this color here, which is what it would set the color buffer to if the second argument was true, but you can't ignore this argument. You have to put something there. Now, there is a fourth optional argument, which is what you set the Z buffer to, but if you don't include that, that defaults to 0. So we're clearing out the Z buffer, but we're leaving the color buffer alone. And I think they leave the color buffer alone because later they draw a skybox anyway. Now remember the light data variables in the HLSL code. We need to set those. We do that via these property ID numbers that we created earlier because that's more efficient than always referring to things by strings. So here we use the set global vector array commands to set those variables, assigning the data from the C# side variables to the HLSL side variables. And then we actually execute this command buffer to run these commands. Then we clear the command buffer so we can use it for something else later. Unity has a sorting setting structure to describe the methods to sort objects during rendering. Taking a look at the different criteria we can sort by, that's not very useful. I guess I got to click on rendering.sorting criteria. Ah, here we go. Let's see, some commonly used sorting combinations are provided for convenience. Use common opaque for opaque objects. This combination of flags includes optimization for reducing drawing state changes and draws roughly front to back to reduce drawing over the same pixels many times. Use common transparent for transparent objects, which need to be sorted from back to front before being drawn for them all to be visible. We'll first draw the opaque objects. So we're going to create a sorting settings variable that has the criteria set to sorting criteria.commonOpaque. This is a C#ism where you can set the instance variables like this during the construction. Next, we'll create some drawing settings consisting of this common opaque sorting setting, and we also need to give it a shader tag ID. Remember, it's this default SRP default unlit light mode, which is what gets run when you don't actually specify a light mode in your shader code. Our C# script knows whether we want to use dynamic batching and/or instancing, but our renderer doesn't actually know that. So we need to tell it by setting the appropriate instance variables here in these drawing settings. And oh look, we need to create another variable. This time it's called filtering settings. So what are those? Let's see. A filtering settings struct describes how to filter the set of objects that Scriptable render context.DrawRenderers receives so that Unity draws a subset of them. And we're giving the constructor the parameter renderQrange.opaque. Let's see. RenderQrange. Static properties opaque. A range that includes only opaque objects. Okay, that was informative. I feel like it would be really helpful if the Unity docs would give us a little more context. Okay, finally we draw some objects. We ask our Scriptable render context to run this DrawRenderers method. The culling results variable is going to contain all of the various bits of information about the objects we need to draw, and it also is going to need drawing settings and filtering settings. These are structures, and for efficiency, instead of passing these by value, it uses reference to pass them by reference. Once we've drawn the objects, we're then going to draw the skybox. This may seem a little counterintuitive. You might think you would first draw the skybox and then draw the objects, but by drawing the objects first, that means it's not going to bother drawing the skybox pixels where there's already an opaque object. Now remember when we cleared the render target and we set some variables on the HLSL side, we needed to do those using a command buffer. But for whatever reason, drawing a skybox is special. You can just ask your Scriptable render context to do that without using a command buffer. Now, the last thing we do is draw objects again, but this time we're only going to be drawing the transparent objects. Now, I haven't been entirely accurate. When I said that we were drawing the opaque objects, and then I said we were drawing the skybox, and then we were drawing the transparent objects, those operations didn't happen right at that particular command. It's basically queuing everything up, and stuff doesn't actually happen until you submit to the Scriptable render context. One thing I should mention that makes working with this scene a little difficult is you'll notice that the lights are in the scene, but they don't have the little light gizmos that you're used to seeing. That's because this is being rendered by our Scriptable render pipeline, and I didn't include the code needed to actually make those little icons appear. If you want to try adding that yourself, you can check out Draw Gizmos. Oh, one more thing. In addition to the MyLit shader we've been talking about, this Unity package also has this Unlit shader, and there's nothing really fancy going on here. It's basically the same as the lit shader code I showed you, except it just returns the basic color.